If you guys remember, way back when we first did law of sines and started using that to solve some triangles, I showed you one example where we sometimes end up with two possible triangles. Today's lesson is when we learn how to tell whether that is the case or not. We still want to be very smart about what strategies we use, but sometimes we will have to say there are two possible triangles, two possible sets of solutions we could come up with. We are going to get into that when, of the three known pieces, we know two sides and one angle. We know the side across from the known angle, so that sets us up. We will be able to use law of sines in there, that we have an angle, and one of the sides we know is across from that, and then we know one of the other two sides as well. So there are three possible things that could happen, and first I'm just going to look at the pictures of what might be going on so we can see when we come up with two possibilities. So these pictures are all in your book, the top of page 558, if you want to be able to look back at that. Remember notation. Capital letters are always the angles, lowercase letters are always the sides, and the A's have to be across from each other, so big A is across from little a in all of these pictures that I have up here so far. One thing that could happen is that we could actually have a right triangle. That opposite side could be exactly long enough to come down so that we would end up with a squared plus b squared equals c squared, and so on. We could have one where one of these sides is too short. There's no way, if this is 40 degrees and this is 9, there's no way this side, even if we come the shortest distance, which is straight down perpendicularly, it's not going to meet that other side, and so no triangle is going to exist. Another thing that could happen is that this side that we know across from the known angle is longer than that straight line distance to make a right triangle. So we're going to have to tilt it a little bit so that it doesn't go past that side. So if we tilt, we could tilt it in and have the triangle that you see here in this third picture, or we could tilt it out to the right so that it looks like what we see in this fourth picture. That is when we have the ambiguous case. The other thing that could happen is that this side across from the 40-degree angles, again, is too long to come straight down and make a right angle, but it is so long that if we tried to tilt it to the left, it would be coming out past that, and then we'd have just some sort of a weird zigzag in here that is not a triangle. So the only choice with that one would be to tilt it way out here to the right so that we definitely have an obtuse angle up here at the top. So those are the five possibilities. And now let's talk about algebraically what we are going to do to check this out. So first we are going to figure out, well, if it was a right angle, if it went the shortest way possible down to make a triangle, how big would that have to be? So again, I know that my A is 40 degrees. My little a is a side that I know across from that. For the notation that I'm going to use here, it does not matter if the side that I know is above or below that angle. I'm always going to draw it above, and it will help me out on grading if you'll just automatically put that up here also. And we're going to call that B. We don't know if this is going to be a right triangle or not when we first start in on these problems. We will then say, well, if it were a right triangle, what would H have to be for that to happen? So H is going to be the height of these triangles, no matter which case we're talking about. If we had a right triangle in there, or if we drew the height down through there, what would it have to be? No matter which one of these triangles you look at, H makes a right angle. So I'm looking at, in this case, a 40, 50, 90 triangle in each of these figures. If I wanted to figure out what H is, I would simply use my SOHCAHTOA right triangle trig. This is the Opposite, this is the hypotenuse, so the sine of, in this case, 40 degrees, or in general, the sine of a degrees would have to be h over 9 in this picture, but in general, h over what I'm calling little b, so that h, if I multiply both sides of this by b, h is b sine a. So that's going to be my first step in each of these. I am going to figure out, if it were a right triangle, how long would h have to be, and it's going to be this side that I know beside the known angle times the sine of the known angle. A little bit of this out of the way as we continue on here working our way through these. Now remember, we have to use standard notation. If we are considering this to be little b right here, that means that the angle across from it must be big B in each case. So you see that I have those written in there. If H and A are the same as each other, then I know, oh, I've got a right triangle. If H is longer than B, or longer than A, I'm sorry, if H is longer than A, then there's no possible triangle. If, for cases 3 and 4, remember that's when we have the ambiguous case, A is bigger than H. But A is short enough that I can swing to the left and not come out here past the A. So if A is short enough that it can swing left or right and make a triangle, we've got the two possible triangles. Well, that means A has to be shorter than 9, or that lowercase b that we were talking about. So for cases 3 and 4, A is bigger than H, so we have to tilt it one side or the other and not go straight down, but A is also shorter than the other side. That's when we have two possible triangles. One with an obtuse angle here at B, and one with an acute angle here at B. Since A is bigger than H and A is shorter than the other side, that means A is in between H and the other side. For the fifth case, there's only one possible triangle. It's going to have an obtuse angle up here for angle C and an acute angle over here for B. Again, A is longer than H, so it has to swing. It can't go straight down. But it's also longer than the 9, because if we tried to swing to the left, it would be way out to the left of angle A. So A is bigger than H, and A is bigger than the other side. Then there is only one triangle. So those are the possibilities. The ambiguous one is when this case 3-4 combination happens, that the opposite side is between the height and the known side that is right beside the known angle. Let's do a couple of examples here. A triangle has a 40-degree angle, so we're going to start out and we're going to draw our known angle over here on the left, and that's going to be 40 degrees. A side adjacent to that has length 9, and we don't know yet really where this is going and which way it's working, but we know that the side opposite has to have length of 4. So we want to try to figure out what is going on. And let's just label some things with our notation. We are letting this be angle A. A is 40 degrees, which means the opposite side has to be little a. And this 9 is what we are going to call side B. Step 1, we learned, is to find, well, what is the height of the triangle if we have a right triangle in there. And we realized that it was always going to be B sine A. It's going to be that adjacent side times the sine of the known angle. So 9 sine 40 degrees. Punching that in on our calculator, we get about 5.785. Step 2 is to compare that opposite side A and H and maybe B, depending on where we end up for this. A is 4, H is 5.785. 4 is shorter than the height. That means it is not long enough to come down and make a triangle. So we would need it to be at least 785 to go down and make a triangle. 4 is not long enough to do that. So final answer for this one is no triangle exists. Okay, got that one done. Nothing else that we have to do. Okay, let's try this one. Draw the triangle or triangles, depending on whether it has one answer or if it might end up being the ambiguous case, and find the missing parts. So for this one, we start off with A has to be 32 degrees. The side across from that is 6. B, the adjacent side, has to be 8. Step 1 is still, let's find what H is. And we know that H is the adjacent side times the sine of the angle that we know. So in this case, 8 times the sine of 32 degrees, which gives us 4.239. Then we compare A and H. And in this case, A is 6, H is 4.239. A is longer than that. So it's long enough to come down. We're going to have a triangle. It's too long to be a right triangle. So we know from that that it has to be from those pictures, picture 3, 4, or 5. So that means we also need to compare with B, which was our adjacent side, which was 8. So in this case, 6 is between that adjacent side and what the height would have to be. So this is the ambiguous case. Meaning we have two triangles, one where we need to swing that opposite side in to the left and one where we need to swing it out to the right, so that we will have our two triangles there. So we need to solve it both ways. Personally, I find it a little bit easier if we first swing it out to the right so that we're going to have an acute value for B when we start doing our law of sines on this. So case 1, I am going to have my 32 degrees here. I'm going to still have my 8 adjacent to that, and I'm going to swing my 6 out to the right so that this will be acute. This was A, this was angle A, this was little b, so this has to be angle big B, this has to be angle big C, and this side has to be little c. So now I need to solve that. Since I know the 32 and the 6, and they are across from each other, I start out with law of sines. So I am going to set this up that 8 over the sine of B is 6 over the sine of 32 degrees. So if I do my cross product, I have 8 times the sine of 32 degrees equals 6 times the sine of b. So if I divide both sides by 6, that will be the sine of b. But what I really want is the angle, so I need to punch in on the calculator the inverse sine of, use my fraction template on the calculator so that I get all of this in the right places. And then I end up with B is 44.956 degrees. Then it is pretty easy to figure out sides or angle C with triangle sum. So C will be 180 minus 32 minus the stored value of B, giving us that C needs to be 103.044 degrees, and we want to store that as C. And let's take a look at our picture here. Yes, that makes sense. If we had to swing the 6 out to the right, we would be getting an obtuse angle. B was our acute angle, almost 45 degrees. That just leaves finding little side C, which we can do with triangle sum, because little side C will have to be equal to our same ratio, so little side C over the sine of our stored C, now that we've figured that out. So that means that we have 6 times the sine of our stored angle C is little c times the sine of 32, so little c will be equal to that divided by the sine of 32 degrees, giving us 11.030 for little c. So let's make sure that we have circled all of our answers that we needed in there. We found angle B, we found angle C, and we found side C. Copy my little c there. And since we know that we're going to have to do 2 cases on this, let's put a subscript on each of these to make it very easy to tell that these are 3 that go together. And then if we can, let's even draw a dividing line so that we can have another section of our problem set box for case 2, for our second triangle. That got us our first triangle. Okay, second triangle, instead of swinging this 6 out to the right, we're going to swing it inside on the triangle so that we will have an acute angle at the top and an obtuse value for angle B. So for our second triangle, we are still going to have 32 degrees here. We are still going to have, how long was that side B? 8 over here. But this time, we are going to swing the 6 inside so that this becomes an obtuse angle B. This is still A, which is the 32. This will be angle C. This will be little side C. We actually don't have quite as much work to do because we know from other problems that we've done, if we had the acute B to get our second possible value for B, we need to simply take the supplement 180 minus that first B that we got. Now this is stored still, so let's just do 180 minus our stored value of B and get 135.044 degrees, and be sure that we store that as our new B. So that is our obtuse value for B. To get our third angle, we still just use triangle sum. So 180 minus the 32 minus that new stored value of B will give us our new C. And in this case, we have 12.956 degrees for our new C. And we want to be sure we store that as C. And this time that's going to be C2. And that makes sense. Now we've got an acute angle in here because we had to swing that 6 inside, so we do get a small angle up there at the top of the triangle. We've got our obtuse angle down at the bottom. That just leaves law of sines now to figure out side C. And we know the 32 and the 6 are across from each other. So we can say that 6 over the sine of 32 is equal to, we're trying to find little side C, over the sine of what we have now stored as C, so it's now our C2. Cross product, 6 times the sine of C equals little c times the sine of 32. Divide both sides by the sine of 32 degrees. And that's little c. Punch that in on the calculator. And little c is 2.538. And that would be little c2, since that is part of our second triangle. And there we have it. We have solved it. It also, notice that C for the second triangle was much smaller than C for the first triangle, which makes sense. This side right here, when we had to swing in to get little c, is much smaller than when we had to swing the side that was 6 long out, and we got a much longer side C right there. And that is what an ambiguous case problem will look like.